My name is Danielle Madras, and this is my course project on the Patent Office presentation. Ammonia plays a key role in sustaining life in the global chemical economy with an annual production exceeding 200 million tons. The bulk of the ammonia is primarily used to make fertilizers for agriculture and to produce explosives, pharmaceuticals, refrigerants, and cleaning products. The Haber-Bosch process combines nitrogen from the air and hydrogen delivered mainly from natural gases such as methane and turns those into ammonia. The reaction is reversible and the product of ammonia is an exothermic product. About 90% of ammonia production worldwide relies on the Haber-Bosch process, which entails thermocatalytic conversion of nitrogen and hydrogen at high temperatures under intense pressure combined with a catalyst to create this ammonia. Little historic background here is that in 1898, Great Britain was facing a food crisis, and researchers were tasked with finding a way to manufacture nitrogen for fertilizers. In 1909, Fitz-Haber discovered that the chemical reaction between nitrogen and hydrogen produced ammonia, which is one of the main compounds in a nitrogen-based fertilizer. Later that year, Carl Bosch got funding to create a commercial-scale machine to produce this ammonia, and the machine was unveiled in 1914. Around the same time frame, World War I was also happening, and they were impacted by this Haber process as it provided ammonia needed for various explosives and weapons. So big surprise here. This process is named after the two creators that discovered it. So Fitz-Haber was born in Germany in 1868 and studied organic chemistry in different German universities. He's pictured here on the right. And Carl Bosch was also born in Germany in 1874 and was a chemical engineer. Between 1894 and 1911, Haber and Bosch developed the Haber-Bosch process for synthesizing ammonia. Lachantière's principle states that when a system at equilibrium is placed under stress, the system will undergo a change in such a way as to relieve that stress. So external stresses are factors that can cause the rate of forward or reverse reaction to change. In the Haber-Bosch process, the goal is to produce as much product, or ammonia in this case, as possible by changing the conditions to favor the forward reaction. The Haber-Bosch process uses concentrations, pressure, temperature, and a catalyst to create conditions that favor the forward reaction. Concentration can be used when the concentration of the nitrogen or the hydrogen is added to the reactant side of the reaction, and then the rate of the forward reaction will increase in order to balance out that equation. Other conditions that also impact the Haber-Bosch reaction are the pressure. So between 200 and 1,000 atmospheres is needed to apply pressure to have the optimum pressure created to produce the amount of ammonia required. Temperature is also impacted in this process. So a temperature between 400 and 500 degrees Celsius is what is typically recommended to run this process. And the final stressor that can add to the rate of the reaction is the catalyst. So without a catalyst, the Haber-Bosch process reaction would be slow, and virtually no reaction happens in an efficient time manner to create the ammonia. The catalyst creates a reaction that is fast enough to produce the ammonia in an efficient time. However, it's important to note that the catalyst itself does not affect the position of equilibrium. In the first Haber-Bosch process, osonium, uranium, and other catalysts were used. Today, the major catalyst used is iron, sometimes potassium oxide, and aluminum oxide can also be used. So the Haber-Bosch process was created about 100 years ago, and it's still the main process being used to synthesize ammonia nowadays. Unfortunately, we now can see the ecological impacts of this particular process. So the fertilizers that this process is obviously contributing to will actually run off and cause water runoff, and then they get into our bodies of water around there, and they affect the algae growth. So the algae grows on top of the water and causes the submerged organisms to die. The algae also consumes all that water's oxygen supply and can lead to dying fish, which impact our ecosystems. This process also consumes 3 to 5% of all of our natural gas produced yearly and produces a huge quantity of greenhouse gases. A lot of research right now around a new electrochemical synthesis. So electrochemical ammonia synthesis can be realized by the reaction of nitrogen and a protein source under milder conditions powered by renewable electricity. This would offer a promising carbon neutral sustainable strategy. Major endeavors are also being developed for a heterogeneous electrocatalyst design approach. This system would be more energy efficient, carbon free, eliminate fossil fuels, flexible for controls to be added to the parameters, and it would also be scalable so you could have on site ammonia production. I do think that this patent should be approved as it would lead to energy saving as well as great ecological impacts in our environment and hopefully, again, reduce that carbon footprint of the Haber-Bosch current process. Here are the references I used for this presentation, and thank you so much for watching.